What's going to happen if we cut this along the center line? And unlike the previous case, it does not fall into two pieces. Now, so far so good. And people might say, oh, I have already done that, and so forth, and it's in books. But even professional mathematicians often don't realize how many twists there are in this resulting object. One, no, maybe more. Two, well, what are we calling one and two? Here we have to remember what we called one. In the original movie strip, I twisted the thing by 180 degrees, and we call that one twist. I'm being a little picky because many mathematicians, with good reason, prefer to call it a half twist, but we'll call that one twist. So, okay, 180 degrees, that's one twist. Imagine that this movie strip, or this strip, is divided into two halves, two lanes, if you like, by the dividing line in the middle. Left lane and right lane. And suppose that you start driving your car along the left lane. If the strip were straight, you would just go around and come back to the left lane and finish, no problem. But we have a movie strip, which means that in the back, this gets twisted and you are sent to the right lane, whereas you started from the left. So nothing doing, you have to keep going, and you keep driving on the right lane, and then you get another twist, and then come back to the left lane and finish. Each time you came in the back, you picked up a twist. So per each circuit, you get twisted once, and you made two circuits. So there should be two twists, you know, one twist per circuit and two circuits. So let's count the number of twists. In this configuration, you see, all the twists are in the upper half of the strip, and the lower half has no twist. Okay, let's count the number of twists that this object has. In order to do so, I'm going to apply the violence, and I'm not going to move, cutting the lower half, and start untwisting the top. One, still twisted obviously. Two. Now it's interesting, we almost convinced ourselves not more than a minute ago that it should have two twists, but actually it's still twisted. So it had actually more than two twists. Three, it's straight but still twisted. Four, and finally it's straight. So the object had four twists, not two. We seem to have proved a moment ago that the object should have two twists, but it had four twists, and it comes from the following interesting effect. In mathematics, you can measure how locally something is twisting, you know, banking this way or that way by using a concept of torsion. You don't have to know what it is, but it's a local measure of how twisted something is. And it is easy to believe that if you add up the local torsion all the way, then the sum is the global twist. For example, here, everything is straight up. So locally, it has no torsion, zero torsion, and 0, 0, 0, if you sum up 0, the result should be 0. That is, if you glue the ends, the global object should have no twist, and it doesn't. But that reasoning is somewhat faulty, because suppose that I go around myself twice. Here, I'm pretty much straight at each point, so local torsion is 0, but does it mean that by adding 0, you get the globally 0 twist? No, because the mere fact of having gone around myself twice produces this twist. Interesting. How many twists? 1, 2. This is a purely global effect. If you go around yourself twice, that's called double cover. You pick up extra 2 twists, and if you go around yourself 3 times, you pick up extra 3 twists, and so forth. So that's where the extra 2 twists came from. The original Möbius argument, as you recall, should have predicted 2 twists because you went around twice, 2 circuits, and each circuit produced 1 twist. But because you went around 2 circuits, that produced 2 extra twists, 2 plus 2, that's 4. That's not what I wanted to show you. What I wanted to show you is something different.
One of several possible designs.
Wow.
Here is a Möbius band. You can see it has this one twist, and this is very simple. It basically, you're walking on this pretty much flat surface,